I think the best way to give you guys the answers of this is doing it out. You could always just jump to the end to see the answers, but I'm going to do it for you. So the first one, what is the water potential of a cell with a solute potential of negative 4.5 bars and a pressure potential of 3 bars? So what's good about this one is all we're going to use is this formula. We don't actually have to calculate that solute potential. We could use that formula for that, but we don't need to. So in this case, we just set it up as psi equals psi s plus psi p. Zoom in a little bit. So it's just negative 4.5 plus 3 equals, in this case, negative 1.5 bars. Always double check. Remember, your answer has to be a negative number. So you screwed up if you get a positive, of course. That's your first one. Next one's the same idea, but they're giving us 2 out of the 3 variables, just different this time. So it tells us the total water potential and the pressure potential. So it's negative 6.5 equals psi s plus 4. So just recalculate out a little bit. You're going to subtract 4 from both sides. And what you end up with is psi s, or the solute potential, equals negative 10.5 bars. Now I'm placing these cells next to each other. So we can say this is cell A, this is cell B. In which way would the water flow? We always say from high to low, or higher water potential to lower water potential. So the water will flow from cell A to cell B. You probably wrote from the cell in question 1 to question 2. That's fine, from high to low water potential. The next one, what is the water potential? It's saying an open container, so that tells us that our pressure potential equals 0. So basically our water potential equals our solute potential. So all we have to do is negative ICRT, and that's going to give us the answer. Sucrose is the other thing we need, so it's negative 1 because of sucrose. C is going to be our concentration, 0.7. R is our constant, 0.0831. And our temperature is going to be 296, because that's 273 plus that 23. We calculate that out, and I believe we're going to get negative 17.2 bars. Next one, a cell is in equilibrium with its surroundings. So it's basically saying that there's no net movement in or out. So we should really have a similar value, same water potential. So outside equals our psi inside. Or in this case, we could have the surroundings and we could have the cell, however you want to phrase it. So what is the water potential of the solution outside the cell? We could really just find inside the cell, same, negative ICRT, because they gave us all the cells information, I believe. Yeah. So our I, in this case, is sucrose, so it's negative 1. Our C is our concentration, 0.45. Our R, 0.0831. And lastly, our temperature, we just have to add those together. That's 307. We multiply that out, and what are we going to get? We're going to get negative 11.5 bars. So that means inside the cell, the water potential is negative 11.5. If it's in equilibrium with the outside, same thing. In this case, it makes no mention of pressure potential, no mention of like plant cell or cell wall. So we're just going to assume that there is no pressure potential, and that's why they're going to be equal. Next page starts to get a little trickier. Okay. So in this case, we have a cell that's in equilibrium with its surroundings, but the cell itself has a pressure potential. So psi, we could say surroundings equals psi of the cell. But in this case, this is just water potential equals, in this case, solute potential plus pressure potential. So what we're going to do here is kind of plug and play in here to get this. So our solute potential, negative I CRT, plug it in. We're going to have negative 2 this time because it's NaCl. Our concentration, 0.55. And our temperature of 24 is going to bring us to 297. In this case, is going to be plus 2. So we get our total calculation here. So if I calculate this out, I got to do this one quick. So it's going to be 2 times 0.55 times 0.0831 times 297. And I'm going to get 27.414 plus 2. So this is going to be 25.1 bars. And remember, negative, silly mistake that we often make. So that's going to be the water potential outside of the cell, negative 25.1 bars. Now we want to figure out what's the concentration of salt or sodium outside that cell. So now we know our overall water potential is negative 25.1. That's going to equal the negative I CRT outside. We plug in, the only thing we don't have is our C. So in this case, it's negative 2 because it's salt, our X because we don't know the concentration, 0.0831, and the same temperature of 297. What we're going to do is divide that 25.1 by negative 2 times 0.0831 times 297. And that's going to give us our X, or our concentration. So if we calculate that out, the answer is going to be 0.51 molar. My biggest question is, does this make sense? Well, yes, it makes sense because inside the cell was 0.55. This one's 0.51. It's very similar. What's the difference? That pressure potential, right? So we have the same overall water potential, but what makes the difference in concentration is the fact that one has a cell wall pushing in. Okay, we'll do number 8. In this case, we have a cell in equilibrium with its surroundings. The concentration of sucrose inside and outside are different. So we have different concentrations. Now we're trying to figure out that pressure potential. So outside the cell is just negative I CRT. The solution doesn't have a pressure potential. It's an open container. That's outside. Equals negative I CRT inside plus my pressure potential. So basically we're going to plug in this, we're going to plug in this, and figure out what the water potential is. So negative times 1, because it's sucrose, 0.5 times 0.0831, and our temperature of 293. Okay. And then we're going to have equals negative 1 times 0.3 in this case, times the 0.0831 times 293. So we're going to calculate each of those out, and we have to remember the concentration of sucrose is blah, blah, blah inside. So for this setup is going to be our plus X, or our pressure potential. And then on this side is just the outside. So when we calculate that out, I could do a quick 0.5 times 0.0831 times 293. Okay, so this side is going to be negative 12.2. The other one is 0.3 times negative 7.3. So the difference here is going to be what our pressure potential is. And in this case, it's going to be 4.9 is our pressure potential, bar. Remember, that's a positive. So 4.9 bars is the difference here. Last one is kind of putting all of this stuff together, and I was tricky because I tell you that there's salt in the solution, but there's sucrose inside the cell. So it's the negative ICRT equals negative ICRT plus 5. That's our pressure potential. We set this up to times 0.3, 0.0831, and then we need our temperature of 290. I did 2 because it's salt. Inside the cell is only sugars, so it's just 1. This is what we don't know, 0.0831, and our temperature of 290. And then it's going to be plus 5. This comes out to be 14.45. Forgot the negative. Equals on this side, I believe negative. Well, I've got to do this just to be sure. Oh, because we need to move some stuff around. Right. So what we want to do is subtract 5 from this side. So then we're going to subtract 5 from this side. And we're going to get 19.45 negative equals negative x times 0.0831 times 290. So we're going to divide that by negative 0.31, 290. I will set that up right now. .0831 times 290. And then we end up with x equals 0.81 molar. So it's telling us the molarity of the sucrose inside is 0.81 molar. I believe that's correct. In the worksheet in front of me, I have quite a different number, but I think it's because I added instead of subtracted that 5. So I believe that's it. I'll double check and I'll let you know. But that's this whole worksheet. This stuff towards the end is probably trickier than anything you would end up seeing, but understanding that, you really know what's going on.